wave motion and alternative forms of wave equation. In this presentation, first of all, we will define wave motion, then we will discuss some important parameter of wave, and then we will express alternative forms of wave equation. First of all, wave motion. Energy can be transferred from a source to a receiver without the transfer of matter between the 2 points through wave motion. Examples are sounds are transported to our ears, light to our eyes, electromagnetic radiation to our television, radio and mobile phones, the waves on the surface of water, etc. Now, we will discuss some parameters related to wave. They are crests and troughs, amplitude, wavelength, frequency, time period, wave number, angular frequency and velocity. For that, let us consider a simple model of the propagation of a wave along the x-axis, which is represented pictorially as a sine function that depends both on time and position. Here x-axis show the direction of particle displacement. The high points on the sine waves are called crests and low points are called troughs. Now the amplitude. The amplitude of the wave is the maximum disturbance of the wave from the midpoint. It is either to the top of the crest or to the bottom of a trough. The amplitude is always a positive number. Now the wavelength. The wavelength is the distance between two adjacent crests or two adjacent troughs or between any two successive identical parts of the wave. See, the distance between two successive crests or distance between two successive troughs or a distance between two successive identical parts of the wave is known as wavelength, lambda. The frequency of the wave is a number of vibrations each part of the wave undergoes in 1 second. Now, next is time period. The time period is the time interval for one complete vibration. It is expressed as T, time period, is equal to 1 upon frequency, or F is equal to 1 upon T. One important thing is that the energy carried by a wave is approximately proportional to the square of the wave frequency. Obviously, higher the frequency, the higher is the transfer of energy in a given time interval. Now, speed of a wave, it is expressed in the terms of its wavelength and its time period or frequency. Therefore, speed or velocity of wave v can be expressed as lambda upon t or it is equal to lambda f. This relationship holds true for all type of wave motion. There may be the waves on water wave, sound wave, waves on string or electromagnetic waves. Now again, two important quantity of wave motion. They are wave number and angular frequency. Wave number k can be defined as 2 pi by lambda. Therefore, lambda becomes 2 pi by k. Angular frequency omega can be expressed in terms of 2 pi f, or f is equal to omega upon 2 pi. Likewise, omega is equal to 2 pi by t and t is equal to 2 pi by omega. Now, alternative forms of wave motion. The equation of traveling sinusoidal wave, which is harmonic wave, which gives the displacement of particle in y direction at some distance x and at time period t, is f of t is equal to a sine omega t minus x upon v, where a becomes amplitude and omega is nothing but the angular frequency of that wave. Now we have this equation which depends on both time and position simultaneously. See, equation f of t is equal to a sine omega t minus x upon v depends on time, and x means it varies with respect to time and it varies with respect to position. Therefore, it is impossible to draw a single two-dimensional graph of a wave function. We have two choices: a graph showing the variation with position at a fixed time, or a graph showing a variation with time at a fixed position. Let's see. This is a graph showing the variation with time at a fixed location. Here, the distance between two crests are defined by the time period t. Likewise, the distance between two successive identical points is equal to nothing but time period t. Same thing can be represented as the variation with position at a fixed time. Here on x-axis, this displacement varies with respect to x, and here the distance between two crests is defined in terms of wavelength lambda. Now, the particles of the medium execute simple harmonic motion when a sinusoidal periodic wave passes through the medium. The equation for a traveling sinusoidal wave, which gives the displacement of the particle in y direction at some distance x at time t, is equal to y is equal to a sine omega t minus x upon v. We had discussed this. Now see, here in this figure shows the shape of wave motion. See, here the sinusoidal wave motion as time passes. Now, each particle on this wave vibrates in simple harmonic motion with the same amplitude A and frequency F. The phases of the vibration are different. See here. Now, when a particle P reaches its extreme position in upward direction, the particle Q, little to its right, is still coming up that phase, and the particle R, little to its left, has already crossed that phase. Here, you can clearly visualize the same. Each particle copies the motion of the another particle at its left with some time delay. Now, see here some time delay. Now, let's understand what does time delay mean. Let's have three such particles on a wave or on a string by name. Let's say P, R and Q. Now, see, P copies the motion of particle R. Similarly, Q particle copies the motion of P particle with some time delay, means after some time. See here you can see this. P copies the wave motion of this particle after some time. See, it reaches its extreme position after some time. Again, this Q reaches at some maximum or extreme position after some time delay. Now, what is this time delay? Let's try to understand. If delta x is the separation between these two particles, suppose the separation between particle P and Q is given by delta x, then if we consider the wave velocity is equal to v, then the Q copies the wave motion of the particle P after time delay of delta x upon v. Again, if two particles are chosen, P and Q, they are separated by distance delta x and the wave velocity is given by v. Therefore, this Q, see, Q repeats the motion of P at the time interval of delta x upon v. Therefore, the time delay is defined as the separation between two particles divided by the velocity. Here again we have one another case, P and W. This P and W, the separation is delta x upon v is equal to time period t, and the particle W copies the motion P after a time delay of delta x by v is equal to capital T. The motion of any particle at any instant of time is identical in all respect of its motion a time period t later. Means if we consider particle P and W, the motion of P and W are identical if they are separated by time delay capital T, means it is equal to time period. So, a delay of one time period is equivalent to no delay. They reach at extreme position together and their velocities are identical at any instant. Now, the same thing is true for a graphical representation of wave which varies with distance at a fixed time. Previous example, x-axis was related with time period t, but same thing is true when we draw a graph with respect to the variation of the position, means the particle displacement varies with distance x. At that time, here the separation is equal to v into t and is called the wavelength lambda. Here, the separation between these two particles becomes velocity into time period, means lambda. Here we can express the delay in terms of wavelength in position. Now, let's try to define some mathematical explanation regarding to this wave motion. For that, let's select two points P and W. They are separated by distance lambda, or you can say the distance, they are separated by time period t. Now, the position of P is x and the position of W is x plus L. Therefore, the separation between P and W becomes L. Again, I would like to repeat. P is located at x. Therefore, the wave equation for P becomes A is equal to sine omega t minus x upon V. W belongs to distance x plus L. The wave equation for W becomes A sine omega t minus x plus L upon V. Suppose the particles at x and x plus L vibrate at the same phases because they are separated by distance lambda. Now let's analyze this equation. See, this is our equation. Now from above equation we can simplify this equation as omega t minus x upon v is equal to omega t minus x upon v, x plus L upon v. We need to add 2 pi, 2 and pi for phase difference. By again simplifying the same thing, we get L is equal to V upon omega 2 and pi. What is L? It is the separation between two points P and W which are chosen. And we have supposed that these particles are in phase, therefore L becomes lambda. Means another thing, the minimum separation between the particles vibrating in same phase is obtained by putting n is equal to 1 in the equation of this equation. Therefore, in this equation, we'll substitute two things. First of all, we'll consider that these two particles are separated by wavelength lambda. And second one, we'll select that they both are successive particles. Therefore, n becomes 1. See what happens when we substitute L is equal to lambda and n is equal to 1. We have the equation lambda is equal to V upon omega 2 pi. By replacing this omega, we put omega is equal to 2 pi f. The equation will be velocity upon frequency or velocity into time period. Therefore, lambda is equal to V upon f or V into time period t. Rearranging the equation, we have velocity is equal to lambda upon time period or frequency into lambda. Therefore, the speed of wave or velocity of wave can be defined as lambda into frequency, wavelength into frequency. Similarly, we can get the wave number k is equal to, now we know that wave number k is nothing but 2 pi by lambda. Now let's substitute V is equal to f upon lambda and omega is equal to 2 pi f in this equation. So our wave number k can be expressed in terms of omega upon V. Now The equation of a traveling sinusoidal wave which gives the displacement of particle in y direction at the some distance x at time t is equal to y is equal to a sine omega t minus x upon v. Let's multiply omega. It goes into bracket and we have y is equal to a sine into bracket omega t minus omega x upon v. Now we know that k is equal to omega upon v. Therefore, the equation of traveling sinusoidal wave in plus x direction becomes y is equal to a sine omega t minus kx. This is equation of simple harmonic motion. Here y gives the displacement of particle in y direction and the direction of wave motion is in positive x direction. If the direction of wave is considered in negative x direction, then here this minus sign is replaced by plus sign. Now, again, we replace omega by 2 pi by t. Now, 1 upon t goes into bracket. I have y is equal to a sine 2 pi t upon capital T minus x upon vt. Again we'll substitute lambda for vt and my equation becomes y is equal to a sine 2 pi t upon time period minus x upon lambda. See, these are the various forms of wave motion. We can use this equation for our conveniency, or we can use this equation to solve some particular problems or some particular numericals. Again, another waveform. Here we have used k is equal to 2 pi by lambda and lambda upon vt. Therefore, now our equation of motion becomes y is equal to a sine k into bracket vt minus x. Now, in wave equation, the origin of time is chosen at an instant when the left end x is equal to 0 is crossing its mean position, y is equal to 0 and is going up. For a general choice of the origin of time, we will have to add a phase constant phi so that the equation will be y a sine omega t minus x upon v plus phi. See here, this is the generalized form of wave equation. Wave is moving in plus x direction. Y is the displacement of particle, and here we have considered appropriate phase constant phi. Now, if the constant phi will be pi by 2, if we chose t is equal to 0 at an instant when the left end reaches its extreme position y is equal to a, then the equation becomes y is equal to a cos omega t minus x upon v. See, this is the another wave equation. Here the wave is moving or is propagating in plus x direction, but the constant phi is equal to pi by 2 and at t is equal to 0, the displacement of y particle is at its amplitude, means it has its maximum value. At that time, we can express the wave motion in term of y is equal to a cos of omega t minus x upon v. See, if the phase is equal, instead of pi by 2, if the phase is equal to pi, then again the equation becomes y is equal to a sine omega x upon v minus t. Similarly, y is equal to a sine kx minus omega t. Thus, we had discussed various forms of wave equations where y is the direction of displacement of particle, wave is propagating in plus x direction, the amplitude is a, angular frequency is omega, x was the displacement, v is the velocity of wave and time at some particular time period. We had introduced phase difference, we had discussed the various value of phase. Thus, here we are very near to end our presentation. Let's have a quick view what we had discussed. We had defined wave motion, then we had described some parameters related to wave, and then we had discussed alternative waveforms of wave motion. Thank you.